This digital map tracks live application nodes processing traffic across two separate geographic regions. When one region goes dark, the incoming data streams don't automatically reroute, they simply drop into a void. Many organizations operate under the assumption that deploying workloads across multiple geographic regions automatically creates high availability. This is a misconception. Expanding a cloud footprint without implementing intelligent traffic routing, aggressive health checks, and rigorous data replication strategies takes your single points of failure and distributes them across a much wider blast radius. Spinning up extra servers in a distant data center provides zero value if the underlying platform lacks the logic to dynamically manage application state and redirect user traffic the moment hardware fails. Connecting infrastructure across regions is only effective when governed by the automated logic required to manage those resources during a crisis. Modern cloud providers operate some of the most meticulously engineered infrastructure on the planet, yet devastating regional outages remain a certainty. Thousands of workloads can drop offline simultaneously due to control plane disruptions, large-scale network partitions, or sweeping software defects introduced during routine maintenance. No region is immune. When a single region deployment encounters one of these failures, the business impact cascades instantly. APIs become unreachable, customer transactions fail, and revenue generation stops completely. The architectural complexity required to prevent this is driven by one specific metric, the Recovery Time Objective, or RTO. This is the strict timeline dictating exactly how quickly a system must recover before the business suffers unacceptable financial or reputational loss. If your disaster recovery strategy is waiting for the cloud provider's engineers to restore power or fix a routing bug, you will almost certainly breach your RTO. For business-critical systems, continuity demands architectures built to detect and survive the total loss of a data center without waiting for human intervention. A functional multi-region architecture requires three non-negotiable components working in unison: global load balancers, stateless application tiers, and actively replicated databases. This diagram maps out a multi-region deployment on Google Cloud. Traffic enters through Cloud DNS and a global external application load balancer at the top. Below that, the application runs on Cloud Run, deployed independently in US Central 1 and Europe West 1. At the base, Cloud SQL handles persistent data with continuous cross-region replication. Under normal conditions, users are routed to their nearest healthy region. But if a massive failure strikes and US Central 1 completely goes offline, the system must react instantly. The global load balancer actively monitors the network. The moment it detects failed regional health checks, it aggressively severs all routing to the dead zone. Incoming user traffic is instantly rerouted to the healthy Europe West 1 deployment. The application continues to serve users with almost zero noticeable disruption. This seamless failover is a carefully calculated architectural state. The infrastructure was engineered to expect the outage. The routing decisions made at the global level depend on the health signals generated within each individual region. Global macro resilience relies entirely on microtelemetry. The global router depends on the health validation happening at the container orchestration layer, typically managed by Kubernetes. This technical reference illustrates Kubernetes health checks. Look at the bottom right. The first line of defense is the liveness probe. A liveness probe is a continuous, automated check asking a simple question: is the application pod alive? If a pod deadlocks or crashes, the probe detects it and immediately restarts the unhealthy container, attempting localized self-healing before escalating the failure. Right above it is the readiness probe. This check dictates whether a pod is actually ready to serve traffic. A container might be running, but if it's still loading data into memory, the readiness probe prevents the load balancer from sending user requests to it. The survival of an entire global network depends on individual containers accurately reporting their localized status every few seconds. Surviving hardware failures is critical, but hardware isn't the only threat. Software deployments are extreme high-risk events that routinely take down systems. Pushing new application versions across multiple active regions requires a deployment strategy that guarantees zero downtime while the code swaps over. This section details the Kubernetes rolling update strategy. It is the default mechanism for safe change management, slowly replacing old pods with new ones. The process is controlled by mathematical logic. Max surge determines how many temporary extra pods can be created above the desired capacity. A setting of 1 means Kubernetes spins up an extra pod running the new code to handle traffic before shutting anything down. Its counterpart is max unavailable. This strictly limits how many old pods can be terminated at the same time. By keeping this number low, the cluster prevents sudden capacity drops during the transition. If the new deployment contains a bug and system performance degrades, this controlled rollout allows for instantaneous rollback capabilities, reverting to the stable version before users notice the error. Systems must survive both catastrophic infrastructure failures and the inherent risks of daily code updates to remain truly available. While stateless application tiers can be spun up or replaced in seconds, the persistent database layer presents a much harder architectural challenge. Maintaining cross-region data consistency is an inescapable physics problem. Data takes time to travel through fiber optic cables, meaning replication is strictly constrained by the speed of light and geographic distance. This chart graphs the operational trade-off required for replication, measuring latency against data consistency. You must choose where your database sits on the spectrum between strong and eventual consistency. Synchronous replication guarantees identical data across regions. It provides strong consistency. However, every time a user writes data, the system must wait for cross-region confirmation before proceeding, which heavily spikes application latency. Asynchronous replication prioritizes speed. It provides lightning-fast user experiences by confirming the write locally and replicating it in the background. But this creates eventual consistency, introducing the tangible risk of data loss if a hard failover occurs before the background sync finishes. This architectural choice links directly back to a business metric, the Recovery Point Objective, or RPO. This defines exactly how much data the company can legally or financially afford to lose in a disaster. Multi-region architecture is not about achieving perfect infrastructure. It is an exercise in choosing which operational compromises the business can afford to make. This flow comparison illustrates the 2 primary deployment models. On the left is the active-active setup, where multiple regions process live customer traffic simultaneously. Active-active yields maximum resource utilization and the fastest possible failover. The trade-off is exponentially increased database conflict complexity, as systems constantly write and overwrite data across distances. On the right is the active-passive model. It offers a less complex alternative by directing all traffic to a primary region while the second sits idle on standby, replicating data and waiting to take over. But active-passive carries a catastrophic danger: configuration drift. Because the passive region isn't actively serving users, manual updates are often missed. When a real crisis hits, there is a high probability the standby environment simply fails to spin up. The only way to mitigate configuration drift is by strictly deploying through infrastructure as code and running continuous, automated disaster recovery tests that force the standby region to prove it works. A disaster recovery plan that isn't codified and regularly tested in production is nothing more than a theoretical vulnerability. These required automation layers introduce a heavy operational tax. Running multi-region means duplicate infrastructure, massive cross-region data transfer fees, and a severely expanded network perimeter. It places an immense burden on engineering teams, who now have to maintain centralized observability, aggregate cross-region logs, and manage sprawling deployment pipelines. Multi-region architecture should never be implemented simply because a cloud provider's dashboard offers a convenient checkbox to deploy in another location. It is a strategic business investment. Every ounce of added complexity must be strictly justified by measuring the financial and reputational impact of potential downtime against the cost of preventing it. The success of a resilient architecture is proven by how invisibly a service continues to function when a major region drops off the map.